Welcome back, engineers. We are discussing common techniques and algorithms in system design, and in this video let's talk about LSM trees. I hope you're ready. Let's get started. So what is an LSM tree? So LSM tree is not any data structure like some of the data structures that we have seen before. This is an entire ecosystem of data structures. So a set of data structures working together really well to give better performance. That's what we are seeing here with LSM trees. So let's try to understand how the system works. So the acronym LSM stands for Log Structured Merge Tree. So we'll break it down and try to understand what these terms mean, right? So first term is log structured, which means we are going to use a logging functionality and we're going to keep appending stuff to a log, right? We're going to have some kind of a file and we're going to keep pushing stuff into the file. Appending is a very fast operation, and we're not going to modify. So that is an important thing to understand with log structured systems. And then we have merge. What we want to do is, as memory fills, merge to disk. We have a data structure in memory. We have a couple of data structures on disk. We're going to put stuff in memory for faster reads. And as this memory fills, we're going to push the data onto the disk, right? So that we can clear up the memory and we can start filling it fresh. And the final term is tree. Tree, because we're going to make use of a balanced search tree in this case, which is hierarchical and sorted and which is very fast for efficient querying, right? So this is the breakdown of LSM, right? Now let's see what are the use cases for this. So whenever you have write heavy databases, we have a write heavy need, we can make use of LSM trees. For example, we have logging where a bunch of logs are being pushed every second. We have time series from different sources, and we can see this in NoSQL database implementations, right? Examples are Cassandra, ScyllaDB, and DynamoDB, right? Now let's see how this LSM tree is structured. So like I said, there are some components in memory, there are some components in disk. So in memory, there is something called as Memtable. So this is the balanced search tree, okay? And this tree will give us speed. And on disk, there are a couple of things. First thing is write ahead log, which is a log. We're going to write ahead to this log and then we're going to push the data into memory. We'll see how the sequence goes in a bit, but just understand that there is some kind of a log on disk. So whenever there is a system crash or database crash, we can recover using this log. We'll just have to roll through the log and keep performing this operation so that we can come back to the original state. And then we have SSTable. SSTable is short for sorted string table, right? And because of this, we're going to get some space efficiency, which we'll see in a bit. And within this SSTable concept, there are some sub-concepts. So SSTables are accompanied by Bloom filters. Because it is a sorted string, we know that Bloom filters are a fantastic technique to check if something is not present in a long set of strings, right? That's why we're going to use Bloom filters, and this is going to give us lookup speed advantage. And we're going to have multi-level structure for SSTables. So as SSTables keep growing, we're going to merge them so that we can save up some space and we're going to get storage efficiency here, right? So this whole ecosystem of things is called LSM tree, right? Let's see how write lifecycle works. So let's say we have some insert request. So first step is to put it in a log. This is write ahead logging. First, we're going to put it in a log and we're going to use append operation, and this is happening on disk, right? And once this is safely stored in the log, we can put it in memory. We have our Memtable, right? So in our Memtable, there is actually a tree, and this can be any balanced search tree like AVL tree, red black tree, or even our B tree that we have seen in the previous video, right? And this is happening in memory, right? So once we have data in this one, this is a limited memory space, right? So it can eventually fill up. So once it is filled up, we're going to make it immutable. So we're going to freeze the tree and then we're going to push everything from the tree to a disk. So this is where we create the SSTable. So this is where we have SSTable on disk. So what we're going to do is create a table in a sorted format. So there are strings against which there are values. So this is a sorted string table, right? So once we have the sorted tables in the background, we can make use of efficient disk utilization like this. So there is a concept called compaction, which works something like this. So let's say we have SS1, which we just got from our memory. And let's say there is another SS1, which we had from the previous step. So let's say we have two SS tables right now. and this is at level 0, the first step, right? So but let's say our threshold is to have a maximum of 2 SS tables in level 0. Once we have this threshold hit, we're going to merge these two tables into a bigger table. So we're going to have level 1, and this is a combination of SS1 and SS2, right? So this becomes L1 SS1. And let's say we have a threshold of 2 L1 SS tables. So once that threshold is hit, we're going to merge these two into L2 SS1, right? We're going to go to level 2. So we're going to make the tables bigger and bigger, and once we have the bigger tables, we can clear up the smaller table so that our space is released, right? So that's what is mentioned here. So whenever a criteria is met, we can merge them. So that's what we meant by merge in the LSM tree concept, right? So once merged, previous tables are deleted to recover disk space. That's what we're doing here. So here is an example of how this compaction works. So SS2 is already available on disk, and SS1 is a new member adding to this storage, right? Now our threshold is hit. We want to merge these two tables into a larger table for level 1. So here is how it will go. So both of these are sorted string tables, right? So we're going to do a comparison. We're going to do a merge sort of multiple arrays basically. So we're going to take element by element, A1 and A2. So both are having the same keys. So we need to make a decision about which key to retain in the final table. So we're going to make use of the newest value because that is the updated one. So we're going to push A1 here. And then we do the same thing for the other keys. We have B2, B2, no change. So this goes directly. And then we have C here, D here. C comes before D because it's sorted. So C goes here, followed by D. And finally, we have E5 removed from SS1 and we have E5 already available in SS2. So what is the newest change? Newest change is that E5 is deleted. So we are not going to retain that in the new table, right? So this way we can merge both SS1 and SS2 into a level 1 merge table. So this is how compaction works, right? So this is the whole write lifecycle. Now let's see the read lifecycle. Now that we have maintained all these structures, let's take the benefit out of it. Let's say we want to search for something called as S, right? And our in-memory table, which is nothing but a balanced search tree, is having this kind of structure: G, E, M, K, P, B, F, right? So this is in a hierarchical sorted order. So first step is to look for S in Memtable. So this is the login operation. We're going to start at G. S is greater than G. We're going to go right to the tree. We're going to reach M. S is greater than M. We're going to reach here, and we reach the depth of the tree. So we did not find our search element, right? So this is O of login operation. And then when this is not found, we're going to go to disk now. So within disk, we know that we have sorted search tables, right? We have a series of these tables because of compaction, but every table will have a Bloom filter attached to it, right? We're going to maintain another data structure, Bloom filter array. We have already discussed how Bloom filters work in the previous videos. So definitely check it out if you haven't done already. So Bloom filters are fantastic for getting a firm no answer, right? We can be definitely sure if something is not present in a long set of strings, right? So we're going to make use of this concept, and at level 0, we're going to ask the Bloom filter, is S available on this table, right? Let's say we're getting a firm no. We still have not found our S because there are only 4 keys here, A, B, and T, and S is not there, right? And we're going to repeat this process on the remaining SS tables. We're going to keep asking Bloom filter. We know that Bloom filter operations are fast, right? So we're going to keep asking Bloom filter on older tables until we get a probable yes, right? Until we get a probable yes. So these operations are O of K. K is for the number of functions used inside Bloom filter. So once we get a probable yes, let's say Bloom filter is saying maybe S is present on this table, right? That is when we actually do the lookup on the physical table. And this is where we use binary search, simple binary search, because we know that our table is sorted string. So we start at the midpoint. We know that S belongs to this half. We go further down, keep going half, half, half. And finally we have our S, which is found here, and then we return S, right? So this is a binary search. Again, this is O of login. So because of all these lookups, search may be a little slower when compared to writes, but writes are tremendously fast, right? So that is a trade-off. So let's see the trade-offs. Faster writes because of sequential writes. We're going to do appends, and then we're going to do in-memory stuff. These are very fast writes. And then we get the advantage of recoverability and durability because we now have write ahead logging and stuff. But slower reads because more disk access is required, and the data is spread across different data structures within disk. And more storage is used for duplication to some extent in multi-level SSTables, and there is also a CPU overhead for compaction. So if you have a write heavy system, you can definitely go for this LSM tree, but the trade-off is that you're going to have little slower reads and more storage requirements, right? So that's all I had for LSM tree, guys. Let me know if you have any questions or suggestions. Thank you so much for watching. Please leave a like if you found this helpful. Please subscribe if you haven't done already. Thank you so much for watching. I will see you in the next one. Cheers.